This is globe-proof backfire number 3. They like to use a Focault pendulum as proof of their rotating globe. So in this video, I'm going to tuck it back into bed so it can go to sleep with all the other globers. Now they say that it rotates clockwise in the northern hemisphere, counterclockwise in the southern hemisphere. They like to try and apply it to bullets and airplanes and whatnot, okay? Here's real Coriolis. Real Coriolis, if something's spinning counterclockwise, you throw something, it'll go clockwise, and vice versa. Now, they always like to express Coriolis in subjective terms like right and left, so for now I'll do that. So you see the merry-go-round is spinning left, okay, we won't call it counterclockwise, and the ball goes right, not clockwise, we'll call it right for now, and I'm going to point out why they do that and how it's demonstrably wrong. So on screen is real-world demonstrable Coriolis effect. Let's hear what Bob the science guy, let's hear his horse shit on what Coriolis is.
Okay, so let's go in and see what the actual Coriolis effect is. Imagine that you have a cannon pointing north, as illustrated in the left side here. Now, the cannonball within it, and the ground it's sitting on are all rotating from west to east at 1,038 miles per hour. When you fire that cannon, you are firing the cannonball in a northerly direction. However, that cannonball is still going from west to east at the same 1,038 miles per hour it had when it was sitting in the barrel of the cannon. Now here's where you run into the problem. Instead of going north, what will happen is the cannonball, which is continuing to go east at 1,038 miles an hour, is starting to go over parts of the Earth that are moving slower than 1,038 miles per hour. Imagine that this is a super cannon and you can shoot all the way from the equator up to the 45th north latitude. The cannonball will still be moving east at 1,038 miles per hour, but the ground underneath it is only going east at 733 miles per hour. As you can see, that will cause the cannonball to arc ahead of the Earth in a curved pattern. You'll get the exact opposite in the southern hemisphere.
Let me give some additional details Bob conveniently left out, which doesn't surprise me in the least. Here's his omissions. So from the perspective of the shooter, the cannonball is deviating to the right, or clockwise. But if he was in the north firing south of the northern hemisphere, it would still deviate to the right or clockwise. Also, if he was above the equator firing south, it would deviate clockwise or to the right, but as soon as it crossed the equator, it would have to then shift direction and go counterclockwise or left in mid-flight. That is ridiculous. So shooting from the north, it would deviate to the right, then cross the equator, and in mid-flight just switch to the left or counterclockwise. It'd look like this. How could anyone possibly believe that? So we'll call this a top-down view of the globe. So no matter heading north or south, we're going to deviate clockwise. So east in one direction and west in the other. Even though the Earth's spinning in one direction, we go east if we're heading north or west if we're heading south.
Someone closer to the North or South Pole will be moving slower, obviously since they don't have to cover as much space to complete one rotation in the same amount of time. So if you're at the equator shooting a target due north, your bullet is not only moving north, but because of the spin of our planet, to the east as well. But due to Earth's curvature, as it moves north, it will move relatively faster to the east than the ground it's flying over. The further it travels north, the greater the speed difference. So by the time the bullet reaches its target, which is also moving east but at a slower speed, it will miss to the right because it moved faster to the east than its target. Now let's say you're at the North Pole shooting south. This time your bullet is moving east slower than your target to the south, so it trails behind. From the perspective of the shooter, it still curves to the right.
Again, watch as the ball leaves Brian's hand. To an observer who's sitting on this rotating body frame, it appears that some mysterious force is accelerating the ball to the right. You can see that from Brian's point of view, the ball seems to follow this quasi-parabolic trajectory to the right. We know from the
Now I want you to pay attention here, because with the roundabout rotating counterclockwise, no matter where they're positioned or no matter which direction they throw the ball, we get a clockwise deviation. So the deviation is always opposite the rotation. And that's real world Coriolis.
Edward is throwing the ball in 4 directions: radially outward, tangentially in the direction of travel, and radially inward here. And you can see that in all these cases, the ball is deflected to the right. Lastly, he's going to turn 90 degrees and throw tangentially in the direction opposite of motion, and the ball still deflects to the right. So regardless of location and direction, it seems that the trajectory of the ball is always deflected to the right when the body frame, aka the merry-go-round, is rotating in a counterclockwise direction. Previous video that Randall, who's sitting on the non-rotating reference frame, just sees the ball fly in a straight trajectory as soon as it leaves Brian's hand.
Like I said, they try to use this as proof. A counterclockwise rotating Earth in the northern hemisphere gives a clockwise rotation of the Focault pendulum and vice versa in the south. However, when it comes to a hurricane, they rotate counterclockwise in the northern hemisphere. And this is why in their demonstrations or explanations, they never say counterclockwise. They always just say to the right. It's lying by omission. And this is where the demonstrations get sloppy. Let's have a look.
Move from the perspective of someone attached to the rotating Earth. So let's jump back to the merry-go-round and make a simulation of this scenario.
Okay, so now let's see if we can simulate the Coriolis effect from a meteorological perspective. So we're going to be using the merry-go-round to simulate the northern hemisphere of the world here. And then
So you can see my horrible cardboard representation of the US and Europe on the merry-go-round, and the X marks the simulated low pressure area over the Atlantic Ocean. Unfortunately, we didn't get a super clean take of this demonstration. It's surprisingly difficult to synchronize 3 people throwing simultaneously on a rotating platform. But anyway, we'll slow this way down to 10% of real time so you can see what's going on. As you can see, from the point of view of someone sitting on Earth in the northern hemisphere, these balls, which represent the air molecules, curve to the right as they move inward. If these were air molecules, eventually they would settle into this counterclockwise spin around the low pressure zone. And if you don't believe this is a real thing, here's a photo taken above Iceland by the Moderate Resolution Imaging Spectroradiometer, or MODIS instrument on board NASA's Aqua satellite.
Well, for starters there, buddy, you're calling this a real photo. Look again, bud. We know this stuff's real until you add a globe. Once you add a globe, it turns into CGI and stories. We know these storms are real. I've lived through several of them. We're doubting your explanation, and it's no wonder you couldn't demonstrate it. If you'd have demonstrated it properly and placed the clouds where the balls would be in relative to the hurricane, all you would have seen is clockwise rotation. There's the only thing you can get in the northern hemisphere. No matter which direction you are throwing the ball, it will go clockwise. Normally, they're quick to use balls in their explanations of fluids. But not when it comes to this, because if we see balls representing the winds of the hurricane coming from the equator, they're going counterclockwise. And coming south from the North Pole, they're also going counterclockwise, exactly opposite of what he just literally demonstrated. So this is why they like to say right and left, and how they don't like to include multiple directions as far as when they're laying it out on their globe. They will when they're showing you on a merry-go-round, because that's reality. But when it comes to their globe, they like to separate them details. They don't like to jumble them all together. It might look a little messy on their globe. And speaking of winds, I left this up on screen. Has anybody noticed that strap that's attached to that saddaloon? Don't it look like a strap that's twisted? Probably from spinning in the wind. I don't know, just saying. And one last point to cover. They would all say that because it's the change in tangential speed, that there would be no Coriolis on a cylinder.
This is true for a non-rotating sphere and a non-rotating cylinder. Once you're rotating both of them, Coriolis is the effect only on the sphere, not on the cylinder. Coriolis is the effect only on the sphere, not on the cylinder.
So if we're standing at the equator on a rotating sphere, and we fired at a tangent, there'd be 0 Coriolis. So if we fire any at all above a tangent, then we'd get reverse Coriolis, because we would then be entering a frame of reference that's rotating faster than the one it left. So it would be opposite of what they claim. They're doing the math calculating the ground speed, but on a ball, as you get higher off the ground, you're rotating faster. So they just really haven't thought this all the way through. So what was meant to be a globe proof turned out to be a globe proof backfire. Thanks for watching.